Okay, good morning, everyone. So welcome to the second lectures of MATH2301. So today we start talking about topic 2, floating point numbers. Okay, so what is floating point numbers? So if you open the computers, yeah, then you will see a motherboard like this, okay? And so under this fan is the CPU. And under the CPU, we have the structure inside the CPU like this. So all your calculation was done inside this floating point units. So now we just focus on the structure of floating point units. So that is the aim. And you see, it doesn't matter you use MATLAB, Python, or C, or Fortran, or C++. They use the same principles because this is a hardware problem. Okay. So now let's start with some simple example. So now suppose I give you a number 50. Okay. So 50 is a decimal number, but then inside the computers, you can represent only 0 and 1, right? So how do you store 50 inside the computer? In the CPU. Well, so we have to convert into a binary number, right? So let's do some simple exercise. How do we write 50 in binary number? Okay, so let me start writing on a piece of paper. So I have a video camera. So I have let me share my camera. Yeah. So can you see? Okay, so now, so how do we find the binary representation of 50? So how do we do that? So find the binary representation of 50, yeah? Binary form of 50. So anyone knows the algorithm? Anyone? Well, you just make a table, okay? You just make a simple table. So you take 50, right? And you divide it by 2, right? And you take the remainder. So x is the number, and modulo x 2, which means that you take the remainder when you divide it by 2, right? So the remainder, when you divide 50 by 2, it just equals 0. And you write 0 here. And you divided 50 by 2, so you got 25. Yeah. And then now you take 25, you divide it by 2, and the remainder is 1. So you write 1 here. Okay. And now you repeat, so 25 you divide it by 2. Remember, you forget the remainder, so you got only 12. Okay. And 12 divided by 2, remainder is 0. And so on. So you got 6 here. 6 divided by 2, your remainder is 0. You got 3, so the remainder is 1. Yeah. And then 3, divided by 2 is 1.5, but you forget the remainder, so it's only 1. 1 divided by 2, it just remainder just 1. Yeah. So then you stop because you cannot do anything more. And now you start to write backward. You start to write backward like this. So you write 50. Okay. The binary form will be 1, 1 here, and 1, yeah, and then 0, 0, and then 0. Okay. And so you can check you can check that this is correct. Why? Because remember, this one is if you expand it, yeah, then this one is power 0. Okay. Okay, this is power.
Do you know where Matthews 1 or 2 is? 102, no, I'm not sure. Sorry, mate.
Sorry. So is it okay? Everything is okay? If you have question, just please type in the chat box, okay? So this is the power of 2, yeah? So now if I write it down, you know, what does it mean? This one just means that, you know, power 0, power 1, 2, 3, 4, 5, yeah? So just 2 to the 5 plus 2 to the 4, okay? Plus, so 0, 0, and plus 2 to the 1, and plus 2 to the 0. So 0 times 2 to the 0. So there's nothing there, yeah? So then this equal, you know, 2 to the 5 is, you know, it's 32, right? Yeah. And this one is just 16, yeah? So plus 2. So it will be 50. So that is how you represent 50 in terms of decimal. I mean, 50. So this one should be base 10, sorry, base 10, yeah? Will be represented by 110010 in base 2 in binary form. So this is the base, yeah? Okay, and in order to convert from binary back to decimal, then you just, you know, trace the power, right? So the first digit just power 0, power 1, power 2, power 3, power 4, power 5. Yeah? So everything clear, yeah? You've seen this before, yeah? Anyone, you seen this before, yeah? So the algorithm is straightforward. So you take 50, you divide it by 2, you take the remainder. So then 0. And then this is the results, it's the remainder, and so on. And then you just write the results from the right. Okay? So 1, 1, 0, 0, and then 1, 0. Okay? And now, what happened if you got a number smaller than 1? Okay, so now the second example is, how do I find the binary representation of, say, 0.3125? Okay, so now you cannot use the previous algorithm because the previous algorithm asks you to divide by 2, right? And this one, definitely you cannot do that. So you need another algorithm. So there is a simple algorithm for you to do that. And the algorithm is, you know, you just take the number x, yeah? And now you see whether 2x bigger than 1. So in the tutorial, I will explain how we come up with this algorithm, okay? But now just use the algorithm first. And then, so now you put in 3, 1, 2, 5, right? So now 2x, is it bigger than 1? So now it's a logical 0 or 1, yeah? So 2x is 0.62 something, yeah? So then definitely still less than 1, so you put in 0, okay? So any question so far? So no question, yeah? So now, you know, you write the results. You write the result is 0.625, right? And now you check whether 2x greater or equal 1. So 2x is 1.2 something, so it's bigger than 1, so you write 1, yeah? And now you have to multiply this one by 2, but then you have to take a y1, okay? So if you take a y1, you know, then this one So you multiply 2, you got 1.25. You take away 1, so you got only 0.25. Okay? And then you check again. So 2x, is it bigger or equal 1 or not? So 2x is only 0.5. So 0.5, no, it's not bigger than 1. Okay, and you do the same. So now the next one will be you see the next one will be 0.5, right? Because you multiply by 0.5, and 2.5 you multiply by 2, then you got 1, so that equal 1. So this one should be 1, yeah. And then you see you multiply by 1, and then you take away 1, so it becomes 0. Okay, and then you can, you know, I mean, here's 0, so you cannot do anything more. So you stop here, and now you write, you know, like from the left, yeah. So 2.315 in base 10 will equal, so it will be 0.01. So you see, so this is after the dot, yeah. So 0 here, 1 here, 0, 1, 0. Okay, so in base 2. So remember, this one is base 2. And you can check that, you see, this one is mean, this is a power. So if you look at power of 2, yeah, then the one right after the dot is -1, and this one is power -2, and this one is power -3, and so on. So this one will be 2 to the minus power 2 plus 2 to the minus power 3. Okay, so where it's just 1/4 plus 1/8. Yeah, you see that this one is 0.3125. So what is the point here? So the point is you can represent any real numbers in a binary form. Okay, so then, but then how do we, you know, like put into the computers? Yeah, so that is the next topic. But before putting into the computers, let me introduce the normalized form. So what does it mean by normalized form? So normalized form is, you know, like you have the first digits. So the normalized form is the first digit will always equal 1. Yeah. So the first digit is always equal 1. So now if you look at this number, yeah, so the first digit is not equal 1. So this is the first digit, yeah. So this one is not normalized. Not normalized. Okay. So how do we normalize it? Well, so in order to make the first digit equal 1, right? You just move the dot here, 2 dots. Yeah, then the first digit equal 1. But when you move 2 dots here, what does it mean? You multiply by 2 to the minus 4. Yes, correct. Yes. So when you move 2 dots here, it means that, you know, you divide it by 4, right? So now you have to put it back. So you have to multiply by, you know, to the I mean you have to put back by multiply by 4 again. Yeah. Okay. So you will write 1.01. Okay. So 1.010, yeah. And because you divide it by 4, so you have to multiply by 4 again. Okay, so this is just a normalized representation. So this is a normalized representation. Okay, so you have some digits, you have some binary. So this one is a binary form, yeah. So you see the first digit is 1, and then you have uh, some numbers here, and you have some power here. So this is the base. Okay. So in general, we can define a normal form, which is like this. So now, you know, the normal form has the form. So this one is very general, right? Because the B can be any base. Okay, but in our case, in the computer, we just use binary form. So B is 2, right? And then the digits. So here the digits come from 0 to B minus 1, but actually in binary just either 0 or 1. Okay, and now, you know, so we have some names. So the digits, so the digits in this form, yeah, D0 is 1. Then the digits, we call it a significant. Okay, so this is the terminology. And E just exponent, right? And then uh, um, the representation is normalized if the first digit is non-zero. Okay, so what is 1 in our case? Yeah. So now what happened is, in practice, you can have infinite many digits. Okay, but inside the computers, you cannot do that. Inside the computers, everything is finite. Yeah. So then we have to reduce this infinite sequence into a finite sequence, and we call it a floating point representation. So this is the floating point representation inside the computer. So you can see that now the number of digits are limited. Okay, so it cut at p minus 1. So you have only p digits. Okay, yeah, because everything is finite inside the computer. And now even the exponent, this is in the some range as well. It only from E min to E max. Yeah. And now we call it, this is a floating point number system. This is how the computers will store floating point numbers or real numbers inside the computers. Okay. And the number P is called the precision. Okay. And the power will between E min and E max, we just call it a range. And IEEE, so what is IEEE? So what is IEEE? So who knows what is IEEE? Somebody from engineers? Yeah. Well, IEEE is stand for International Engineering something. You can Google it, but it's an engineering organization. Okay. So first it was in the US, but now it's become international. So it's an organization that define the standards for electronic devices, you know, back in the 70s and 80s, and maybe still up to now. Okay. And IEEE, I think they are the first one who decides, you know, like how the floating point number system should be inside the CPU of the early computers and early CPUs and until now. Okay. And they have only two types, two major types: single precision and double precision. Okay, so what is the difference? So the single precision, they use 4 bytes to store floating numbers. Okay, and 4 bytes is 32 bits. Yeah, and you know, double precision, they use 64 bits, 8 bytes. Yeah, 1 byte is 8 bits. Yeah. So the terminology bytes and bits was given by them in the 1970 as well, around that time. Okay. And you see that nowadays you still see Windows 32, Windows 64, some cryptic directory in your Windows machine. And it just means that Windows 64 use 64 bits to address the memories. Okay. And Windows 32, the earlier version of Windows back in the 80 or 90, they use 32 bits to address the memory. So now, so now we will look into the double, I mean the floating point number system more clearly. Yeah. So now the structure look like this. So you see 64 bits, okay, or 32 bits will be divided into 3 parts. So the first part is just 1 bit, and this bit, give you either plus or minus. So it's a negative or positive number, okay? And then the next part, okay, give you the exponent. So remember in the example, the exponent, now they store the exponent here in that part. And then the last part, they just store the fractional part of the significand. So why is that? Why they store only the fractional part? Why don't they store the whole significand? Anyone? So why they store only the fractional part of the significand? So remember the significand is the whole sequence d0 dot d1 up to dp minus 1 here. But they say that they don't store d0. They store only d1 up to dp minus 1. And why is that? Anyone? Any guess? D0 always has to be 1. Yes, exactly. So you see, that's why they, define the normalized number. So the normalized number, then D0 is always 1. So they don't have to store D0. So save 1 bit. Yeah. Okay. And that's exactly right. Yeah. So now you see that is the next sentence here. So in binary normalized representation, only the fractional part is stored because the leading digits is always 1. Yeah. So then in the single precision, then the exponent field is 8 bits. Okay. In double precision, then the exponent is 11 bits. So now you think about this. So if now forget about single precision because we don't use single precision, very often. So in MATLAB, we use double precision. So now when you have exponent field is 11 bits, then what is the range of the exponent? So what is the range of exponent? With 11 bits, how many values can you do? Remember, everything is binary. So with 11 bits, how many values you can store? Okay, so how about with 2 bits, how many values you can store? Well, okay, it's correct, yes, 2 to the 11, yeah? So 2 to the 11 value. So 2 to 11 value will be 2048 values, yes, of exponent. Okay, so remember these values we will discuss next slide. Yeah. So now, this is another concept is the machine by epsilon. So machine by epsilon is you take the binary floating point number representation, okay, and then if you take the difference between the next machine number, okay, and number 1, then you see that it equals 0.0001, and then it will be 2 to the 1 minus p. Yeah. So maybe go back to the floating point representation. Yeah. So then I will explain a bit more here. So now we go back. Let me share the document projector. Yeah. Okay, so now you go back to the so you see you have free field like this, yeah. So this exponent, yeah, plus or minus, and this one is exponent, yeah. Okay, and now what is the so this is the fractional part of the significant, yeah. So now suppose I take number 1. So how do I store number 1 in this form? So number 1. So remember 1 here is in the decimal form, yeah. Okay, then 1 will be, so the plus or minus, so it's a plus, yeah. So then the first digit is 1, okay, and then you have all of them are 0. So on the fractional article 0, yeah. But then how many digits? So remember, if we remember in the double precision, then this one is 1 bit, okay, and then you have 11 bits here, okay, and then how many bits in the fractional part? So remember, in the double precision we have 64 bits in total, yeah. So then this one should be, so this is 12, yeah. So this one should be 52, right? Okay, so then this one will be, like the first digit, the second digits, up to the 52 digits. Yeah. And now, so remember, this is just a significant part. Yeah. And now suppose, so remember your odometers in the car, right? So when you run to the next kilometer, then this one will turn to the next number, right? I mean, the very last digits is turn to the next number. So here the same. So now suppose, you increase the number, the last digits, yeah, then this one will become 1. Okay, so this number, and everything is still equal 0. Okay, so the first one is still 1. Okay, and here they call it 1 plus epsilon. Yeah, so epsilon is just the gap between 1, yeah, between 1 and the next machine number. So 10 here just means base 10. Yeah, and you see, so the difference will be, so when you take the difference, so then you say that epsilon will be just, like the last digit will be 1 over 2 to the 52. Okay, so what is 1 over 2 to the 52? So if you use MATLAB, you will see that. So now if you go to MATLAB, yeah. So let me Let me share you the MATLAB. So if you go to MATLAB, okay, so you type in 1 over 2 to the 52. You see, so 2.2 e to the minus 16, yeah, you can see it. Yeah, but now if there's a command in MATLAB called epsilon EPS, yeah, and you see exactly the same, okay? But now look at this one. So now if I take 1 plus epsilon over 2, yeah, and I say that is bigger than 1, is it correct? Now by calculus, it should be correct, right? Yeah? No. Okay, you type it in, yeah? Yes, so say no, yeah? And why is that? Well, because you see, epsilon is just the gap, right, between 1 and the next machine number. No, it thinks epsilon equals 0. Yeah, because it thinks epsilon equals it thinks epsilon over 2 equals 0. Yeah, because epsilon is a small gap between 1 and the next number. Okay, so epsilon over 2, it's just so small that, you know, I mean, it just assume it's equals 0. Okay, so you say that 1 plus epsilon, then it will be okay. Yeah, it's equal 1. So yes, there's not enough bits. Yeah, so you see, so that is the limit. Yeah, so epsilon is the smallest number you can get. Okay, in the floating point number system. And now there's another concept called real min and real max. So now let me show you the diagram again. Yeah. So now remember we have you know, like the scheme here. So what is the maximal you can get in this representation? So in this representation, again, yeah. So now we go to this scheme. Okay. So I say that this is a maximal number. And if a maximal number, then you see, I mean, if you think of your car again, and everything should equal 1, yeah? Everything should equal 1. Okay. You know, I mean, because remember it's a binary, so the binary, the maximum number is equal 1, right? That in your car, you know, you can become 99999, but in this CPU, everything just equals 0 or 1. So the maximum you can get is everything just equal 1. Okay, but now what is that in terms of decimal? So suppose we call it a real max, yeah. Then okay. Then if you write down in terms of floating point representation, then the first digit is equal 1, okay? And then 1, 1, 1, 1, 1, and 1, and 1 up to the end. Okay, so remember there is 52 digits. Okay, and now do not forget the power. So now you have to multiply the power. Okay, okay, so now this is an interesting question. So what is the maximal power? So remember before we said that there's 11 bits here, yeah? Okay. Then what is the maximal power you can get? So what is the maximal power you can get? 11,111, yeah, but 11,111 is what? So now I want to write down in terms of, yes, okay, in terms of binary. Okay, it's 2048. But actually, because remember, you know, in the real system, you can have negative power as well, right? So you don't want only positive powers, okay? So now IEEE decided that, 2048 values will be distributed, to negative and positive power. Yeah. So then they have the E max will be, so that the range of E, yeah, the range of E, I will write down, yeah, in IEEE, yeah. So will be between E max, and this one is E mean, and they decided E max will be 1023, okay, and E mean will be minus 1022, okay. So you will see that, I mean, it's not exactly 248, yeah, because, you have 100, you have only 2045 here, so 2046 here, okay. So there's only two values left. So two values left are reserved for something like, non-normalized number, for not a number, for infinity, minus infinity. So you can read more details in the lecture note, but the key point is that Emax is only stopped at 1023. Okay, and now the real max. Okay, so now the real max, what is the real max? If I put it in everything here, then I will write down, this one in terms of my, so this one is in binary form, yeah. So now in terms of decimal, then this one will be 1 plus 1 over 2 plus 1 over 2 square, yeah, plus dot 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 up to 1 over 2 to the 52, okay, and then multiply by 2 to the 1023, okay. And then, if you remember first year geometric sequence, yeah, so then what is this number? So it will be 1 minus 2 to the minus 53, 1 minus 1/2, right? Times 2 to the 1023, okay? And 2 minus 1/2 is 1/2, and you flip it, so it becomes 2 times 1 to the minus 53, 1023, okay? And now, this one will become like 2 minus 2 to the minus 52 times 2 to the 1023. Okay, so now I want to put this number into MATLAB and see what do I get. Okay, so now, so suppose you remember the formula already. So now let me put into MATLAB and try to evaluate this number. So I put in 2 minus 52 and 2 raised to the power 123. Okay. And now in MATLAB, if you type real max, you get the same, you see? So what is this number? So this one is the maximal floating point number you can put in MATLAB, or you can put in any double precision system, Fortran or Python or whatever. So beyond this one, then you got a overflow. Okay. so that is the limit of MATLAB. So beyond this one, then you just got infinity. So suppose I take real max, yeah, plus say 100 or maybe plus 1. or maybe no, plus maybe 100 or something, 1000. That's still okay. But well, maybe let me take like exponent of like 700. Still okay, maybe 800. Yeah. See, it become infinity. You see, so somehow, you know, I mean, if it by on real max, then it's become infinity. So I mean, if 750 is infinity already. So maybe 720, infinity, 700. 700 is still okay, yeah. So 712, so 710, 709. You see, so 709 is very close to real max already. And then after that, so you see the limit. So you cannot go by on the maximal value that MATLAB can handle. Otherwise, you got overflow. Okay. So now let me go back to the slide. Yeah, and there's a real mean as well. And you know, you can use the same principles. So real mean, then you just take everything equals 0. Yeah, except the first one. So now let me show you there is you know, so there is a disaster in the military, I mean in the US military, that related to this binary system. So maybe it's better to watch the video. They explain it very well. Yeah. So wait, let me share the screen. Stop this and share the screen of my YouTube. Engineering disasters on modern marvels. We have to stop here, but I think I will post a link and you can watch it because we don't have a lot of time. So, but the videos will explain what is going on, you know, when you forget to convert the numbers correctly between single precision and double precision. Okay, and another is related to you know, you cannot expand 0.1 by finite bits, by finite many bits in binary form. Okay, so now so we talk about real max already. Yeah, so real mean. So real mean is, yes, so you can put everything equals 0. Yeah, and E mean is like I said before. So E mean will be for the double precision will be minus 1022. Okay, and you plug it in. And why we have a number 1 here? So number 1 here because what? Why we have a number 1 here? So we put everything equals 0. Yeah. But why we have a number 1 here? Anyone? Are you still around or? Yes. Why is that? Because. So what is the keyword? Because we said that it's a normalized. Yes, because we said a normalized machine number. So the first digit has to be equal 1, and we never store it. Okay. So real mean is not actually 0, because remember, if you put 0 here and everything is equal 0. Okay. So this one just real mean is just a minimal normalized positive machine number. Okay. And you put it in and you got something, you know, very small. Okay. Okay, and if a number smaller than real mean, and then we say that is underflow, and this one is related to the Ariane rocket incidents. So please watch it when you have time. And if computation is over real max, then we say that overflow. Okay, so that is overflow. So this one explains why the rocket exploded. And see, I mean, there's some very simple problems and people just ignore it and then it's exploded. So it cost them like billion of dollars. Okay, so I mean, we have to be careful. Okay. Okay, so now there is another phenomenon with related to the floating point number system. So now maybe I let you read the question and then go to Google form and answer. Okay, so now suppose I have x equal 0.12345678, and then I repeat 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Now I just take away the first 9 digits after the dot. Okay, so minus 0.123 up to 9. Yeah. So by simple calculation, yeah, elementary calculation, then x should equal the last 9 digits. I mean, the first 9 digits become 0, right? But now, is it true or not? So we go to the Google form. So if you go to the Google form designed to make sure that you're still awake. It's only 11 o'clock, but who knows? You might stay up late until 3 a.m. last night, So if you go to Google and you click on the floating point numbers, yeah, you will see 2 questions. Okay. And so I will show you the results of the survey. And let me go to the survey. I can share the screen. See how many people still awake. Okay, so I can share you the screen, yeah? So we have 5 people still awake, okay? 6, good, okay. So we have, so see for the first one, because we've discussed it already, so real min and real max, so there is no contradiction. I mean, everyone agree with these values. But now, so this one, we have, like a difference here. So 10 people, 7 people say no, and 3 people say yes. Okay, so we have a democracy here, yeah? So now, so we have at least 10 people still around, yeah? At least, or 11, okay, so it's good. But we don't have a majority, okay? So because we don't have a majority, so, 12, okay. Well, we have a majority, yeah? But we don't have like a unanimous answer. So let me put into MATLAB and I will show you the results, okay? So if I put into MATLAB, so you can see my MATLAB is right here, yeah? So now if I put in x is 0.123456789, then 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah? And then minus, okay? 1, 2, oh, sorry. What is the question? So I just type in 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Yeah. Then now I say that x is it equal 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. The answer is 0. It's not true. Okay. I mean, you're supposed to get, I mean, supposed to get it. X has to be like this by simple calculation, but it's not the case. Yeah. So you see that. So there is something going on here. Okay. And the next slide will be what is going on here. So let me stop the MATLAB, and I want to share you the slide again. So you see, so there's something going on. It's not exactly as you expected. Yeah. And now we will let me draw pictures. But you see that when you have infinite many digits, when you put into machine, you can put only finite many digits. Remember, like 52 digits after the dot, for example. Then it introduce some errors. Yeah. So that is, we call it a rounding errors. And maybe it's better to draw pictures. Yeah. So the x plus and the x minus. So the x plus and the x minus look like this. So if I don't have a pictures here, but let me draw pictures real quick. So back to the paper. So now suppose you have a real number. So remember, real numbers, you have infinite many numbers. Yeah. And then I mean, the numbers inside the floating point number system is just finite many numbers. Yeah. So it can be denoted by some dot like this. Okay. And then now suppose you put in x equal pi. Okay. Yeah. So suppose I put x equal pi here. So remember the bar, the vertical bars are machine number. So suppose I put x equal pi here. Right, x equal pi here. Yeah. Then the number right before the machine, so this is the machine number right before x, we call it x minus. Okay. And then the number right after that, we call it x plus. Yeah. So you see that you cannot store x exactly in the computer. What you store is only x minus or x plus. Okay. And then you will introduce some errors. So the errors will be x minus x plus, or x minus x minus or x minus x plus. So we call it a rounded errors. Okay, so that is the definition. So formally we have formula like this. Yeah. So x plus is just the minimal number that greater than x, and x minus the maximal number less than x. But you can see it in the pictures in the diagram. Yeah. And then you can even expand it in terms of a floating point number system. So remember, b here just 2 binary, b just equal 2. And so now this one is a simple example, right? So suppose you have pi. Pi is this, in decimal. You have infinite many dots here. And then when you expand it into binary, it has infinite many digits after the dot as well, right? And the x minus, yeah, it's just that, well, here we just assume that we have only 3 digits. So p equals 3, so you have only 3 digits, so you stop 3 digits. Yeah. And, you know, I mean, so that the x minus is just this number. Okay, you just take 0 here. And when you write down in terms of decimal again, it's just 3.0. And x plus is, again, because we can use only 3 digits. Yeah. So you have to round it up the last digits. So you got 11.1, yeah, in binary form. And when you rewrite it in the decimal, that is 3.5. You see, so this number is slightly bigger than pi, and this one is slightly smaller than pi, you know, within your system. So remember, the binary b equals 2, b equals 3 means that we have only 3 digits in the system. And this is a minimal, maximal, you know, exponent, okay? So maybe we stop here, and then, you know, next time we talk about the reason why you don't have what you expected in the motivation survey. Yeah? So we stop here, yeah? So any question? So let me stop my recording, and then you can ask questions.